All right, it's working. All right, so what context have you seen this come up in?
Context.
Oh, what context?
It's usually like synthesis reactions.
Mm-hmm. Uh-huh. Okay. What can you tell me about it?
I know it's like like carbonyl stuff reacting as like reagents. You have like an aldehyde or like a ketone or like one of each or the same. Um, and it's a synthesis reaction.
How do you know it's a synthesis reaction?
Um, well, it's a condensation reaction. I'm thinking so like two things joining.
Uh-huh. So tell me more about condensation,
Um,
because it's a specific type of um synthesis.
yeah, so when I am thinking of condensation, I'm thinking of water.
Yeah.
Like the opposite sort of hydrolysis.
Yep. So what's another name for it for condensation?
Um, Dehydration.
Huh? Dehydration synthesis.
So,
Because the synthesis part means you're combining, right?
yeah.
So, okay. So, um, you're going to have a okay, so let's see if we can talk about so okay. This is going to be a reaction where uh that's different from ones that we typically see because typically, when I talk about these reactions, I talk about like something like a hydroxyl group acting as a nucleophile.
Mhm.
But for the aldol condensation, so I say like in organic chemistry that nucleophile is a Lewis base, electrophile is a Lewis acid, um, and that we usually don't use the Bronsted-Lowry definition of acid and base, which is an acid gets deprotonated, a base gets protonated. But for the aldol condensation, that is what you'll see. You'll see a base act as a base and not as a nucleophile. So, and that is also so the reason for that is because the so if I were to draw like um I'll draw like a ketone. Um I'll draw it like with another like carbon there. So here, so okay, I'll just say like R1, R2. And so for this carbon here, going like whatever into the page, you have a hydrogen coming like out of the page, you have a hydrogen. So what happens? So these are called alpha hydrogens. And an alpha hydrogen is a hydrogen that's attached to a carbon, which is attached to a carbonyl. So you can imagine it's essentially like the induction effect of the oxygen electron withdrawing group. So it pulls the electron density towards itself, making it so that the hydrogens don't have much electron density and they will want to leave and form a new bond elsewhere where they could gain where they can have more of their electrons.
Okay.
So I believe the pKa for alpha hydrogens is like I think it's like maybe like 17 or something like that. Um, like between 17 and 19, which uh which I guess oh, that looks like a Yeah, so I guess, yeah, so that's not really, I don't know if we talked about like how pH and pKa are different. Like pH is based on the autoionization of water, and that's why with pH you get like pH of 1, pH of 14, right? But in actuality, the pKa is more of an intrinsic measure of that for a molecule. So you'll see that pKa, like strong acid pKa's, will be like less than 0, you know, um, like negative, and you'll see uh like strong base pKa be like 50, something like that. So this pKa of 17 to 19 makes it weakly acidic. So, and if you have something that's weakly acidic, all you need is when you add a strong base, that base will deprotonate one of these weakly acidic hydrogens, right? So that's kind of what essentially happens. So you can have okay, we can have this molecule, and we can have, I'll just draw like a plus sign, and let's have it be another, I'll say R3. I'm going to draw just another ketone.
Mhm.
And I mean, before I go into like the mechanism, I just want to show you the overall reaction. So this is going to turn into this and H2O. So we are essentially combining these two molecules and making a double bond in the process to bring these things together. So um so this can be useful in that it can make a beta keto um like ester, but like or yeah, so here, I guess I'll go into like maybe the mechanism, but the idea, let me get a mechanism. Okay, so I'm going to draw the mechanism underneath. So I'll do the base. You could also use an acid to catalyze this, but I'll draw the base one first because that's usually what happens. So let's say we have, um, yeah, let's say we have something like this. That, and let's add methoxide. And what that will do is, instead of doing this like we are used to seeing,
Yeah.
it's going to take that alpha hydrogen, right? And so it's going to take that, and the electrons that form the bond with the alpha hydrogen will go here to form a double bond. And the oxygen double bond will go up towards the oxygen itself.
Okay.
right? And then so you'll then see um something like this. So with that double bond here. Now this is called the enolate. Okay. So
Yeah.
um so so like it kind of, so whenever you learn about, well, like a charged version of something, particularly when it's like an acid that loses its hydrogen, it then becomes whatever that name is with an ATE at the end, right? Like yeah. So okay, we have our enolate here, and you can have another um so okay, then we'll have this reforming that double bond. And then the double bond that we have here will react with another version of this molecule. Well, another molecule like that's already present. So N1, I mean R1, this, R2, and this will um form a bond with that over there.
And so like does that carbon of like the end on the enolate, does that carbon when the double bond reforms, does it get a negative charge
Um,
and then attacks, or like or is it yeah.
so okay, what you were asking about um the so wait, sorry, tell me what you were asking again. I'm just gonna
In the enolate, in the enolate, you said that the negative charge is on the oxygen is going to reform, like the electrons are going to jump in and reform that double bond. So the carbon can't have like, that many bonds. So is it going to like create like a negative charge on that like carbon that's closer to the R2 end?
yeah, so I guess I kind of like skipped a step here, so let me just put that in. So yeah, so this oxygen is going to reform that double bond, and then the electrons from this double bond will go to this carbon here. So this would be this double bonded here, R2, and then this side will have, as you said, a negative charge now.
Okay, I
So,
see.
mm-hmm,
And then that nucleophilically attacks.
uh-huh, yeah. So then,
Okay.
uh-huh,
So like the first step is, I think they call it like charging it or like activating.
uh-huh.
I'm not sure. Um, so that OCH3, that's just a base, right? So like 1 unit of a base. Okay. And it could be any base, or I guess
It must be a strong base.
strong base.
Strong base. Think of it like this, like if it's a weak acid, to get it to behave like an acid, you need a strong base. If it's a weak base, to get it to behave as a base, you need a strong acid.
Okay.
So yeah. So okay, we're gonna have, yeah, so we're gonna have this happening, and there's actually, well, I'll go over like, because okay, so basically, um so the enolate is that anionic compound, and it's going to then nucleophilically attack the carbonyl like we usually see. And when it does that, it will create a beta hydroxy, a beta hydroxy carbonyl compound. So what I mean by that is from here, if we add another one of these same molecules, like the R1, this thing, R2, like that, we can have our nucleophilic attack there, pushing that over there.
Mhm.
And then so then you would have this R1 and then so since it's attaching this carbon here, the R2 will stay. Well, let me make sure actually. So a bond will be made between let's see. Let me make sure that one of these R's leave. Okay, so okay, so yeah, so the R, so that okay, so this over here would bind to that oxygen. So I would draw the oxygen as well as the um the attach that to that R2. Okay, it should look something like this. Let me make sure over here. Okay, so I'm gonna add for the enolate, there is keto enol like tautomerization, or rather not exactly. This is more so actually just resonance. So we can have this also look like well, all right, whatever. I'll just do the resonance part after. So okay, we have, let me just do this. This will be easier. So okay. So we have the base cat. Can you see the image I pasted?
Yeah, I can see it.
Yeah. So okay, so what we have here is, so over here we have our aldehyde. All right. And here we have a strong base. right? Like sodium, like whatever hydroxide.
Yeah.
And it plucks off that alpha hydrogen that's weakly acidic, forming that double bond there. And we get our enolate here. And the enolate can undergo resonance. So when like this thing comes back down, it will push the electrons from this double bond here to make that negative carbon.
Yeah.
And then that negative carbon can act as a nucleophile, and it can attack another, like one of these starting molecules, um like the starting aldehyde. And when it attacks that, it's going to form this structure here.
There, I have a question there.
Yeah,
I
yeah.
always get confused. So the carbonyl that is retained, is
Mhm.
that from the aldehyde that was initially like deprotonated, or is that the one from the second unit of second molecule?
Yeah, so when I was drawing this, I was trying to figure that out myself because it can kind of get confusing here. So okay. What we should have happened though is uh so wait, sorry, you were asking about the oxygens. You're saying which oxygen stays and
Yep.
huh?
Yep, like which is the carbonyl and which is the um that which carbonyl is retained.
Yeah, got it, got it. Yeah, so the initial carbonyl will be the one that's retained because that carbonyl does not undergo nucleophilic substitution or anything like that.
Okay,
But
okay. I see.
yeah. And then when you add that the next oxygen, that's going to be not a carbonyl anymore because you're nucleophilically attacking it.
Okay, I see.
Uh-huh. So yeah. So basically, um, so this I'll make orange. That's orange, and then I use like pink for this is the second oxygen, and that's that oxygen right there,
Yep.
right? So yeah. So basically that's what happens, and you then get this molecule, the over here, um, which is which has like a negative charge, right? So
Yes.
in my drawing, like, it should be like over there. And now what we are going to do here with that negative charge is we're going to have it act as a base rather than a nucleophile. So that's why, and this is where the so yeah, it'll pluck off a hydrogen water, from a water molecule, and
Mm-hmm.
then it will give us our aldol, which makes sense because you have an aldehyde portion and an alcohol portion, right?
Yes.
Good. So yeah, so that's that. And let's talk about, I guess, yeah, because like I was kind of gonna draw like every step of the mechanism, but it's easier to just kind of see it here. But if you
Yeah.
wanted to also think of a way to like a shortcut to do something like this, you would get, oh, and then so I guess the one that I was drawing here, I started off with a ketone. So you could also just have that. Yeah, I think I think I overcomplicated it by making, I'm gonna draw this just one more time to make it better. So R1, R2, instead of, because I had like, this thing over here that made it messy, but I'm just gonna start off with this much more regular compound. With R2, I guess I would just turn it into like CH3, let's say, and we add our methoxide, which will whoops. So we have that. Then this plugs that off. That goes there. This goes here. And so then we get our yeah, basically just that. And then whoops, when this comes back, this goes here. So then you get I'll just put a negative charge there. And then another one of the same molecule. And this time nucleophilically attacks that. So you get this. And then from here, that's when you would get the oxygen, the R1, and the R2. Right? And then you get, oh, and then this is the, what did I call it? Beta keto ester, something like that. But I'll just move on to the next step. So then it will, this,
It will act as a base.
yeah. So yeah, that's what that would look like. And yeah, and then that's the aldol because it has the aldehyde. Well, I guess I used a ketone here, but same kind of thing. Um, but what happens, or actually, this should be then called a beta hydroxyketone.
Mm.
So yeah, so you have that. And then what happens, let me see. So, okay. Yeah, so then what happens is an elimination reaction, which means that the OH group leaves. Let me see if they have it here. Okay, yeah, they have it here too. So the base-catalyzed dehydration. So so we start from that aldol, and a base removes the alpha hydrogen, and this alpha hydrogen is the alpha hydrogen of two, I mean, I guess one is a alcohol group and the other is a carbonyl, but that's a very like a weakly acidic hydrogen there. So basically from this point, right, I can write so yeah, so one of these, so let's see, I can write down like an H here, and base will pluck off this H, and then the electrons go to make that double bond.
Yep. I see.
Yeah.
That's a bond. And OH is the leaving group.
Uh-huh. So yeah, so then we get that. And that negative charge is gonna like form a double bond here. And yes, the hydroxyl will leave. Giving you R1. Something like that. So this is um the alpha. So okay, yeah, this is the alpha beta unsaturated ketone. So yeah, so that's what that looks like, and then this is what it would be for the. It's essentially the same thing. We just have another R here for the ketone.
Yeah.
Right. So okay, that's the mechanism. Now, what can we do to be able to do this faster without doing the mechanism? So one of the tricks that you can do, and this works for like, any type of condensation reaction, is if you can like, so I'm gonna draw like put like H2O in like a box. So like what I mean is, let's say we have this CH3 CH, and then two alpha hydrogens here, and another identical molecule that gets added to it. And this, whoops. See how I put these two alpha hydrogens and the carbonyl oxygen together? Like when I say together, sorry, I mean like I just made it so that they're lined up, and in that blue box, that's
Yeah.
like that. So
Yeah.
we're gonna get rid of that because that's gonna turn into water, right? So
Yes. Yes, that's correct.
this will ultimately give you that.
Yeah, I see how you got rid of water.
Yep. So that's a shortcut way of doing it. So you wanna essentially you're going to be losing uh so essentially you're going to be deprotonating an aldehyde or a ketone, and that aldehyde or a ketone will that's deprotonated. Once it's deprotonated, it'll be called in like an enolate, and and it's it can have a negative charge on like the carbon that the alpha carbon, and that can nucleophilically attack another identical molecule and thus form a bond with it. And once you do that, you're going to have like your carbonyl group, and you'll have an alcohol group, and that's the beta, or no, that's the aldol. And then you add base again, and you're going to have the OH group leave, and you'll have your alpha beta unsaturated molecule.
I see. So in total, you use, because I remember this also being important, like we use 2 units of a base.
I think here we have this base added. And here we're deprotonating H2O, which should be that. So
I see.
the thing, yeah. So the thing with yeah, so the thing with base catalyzed stuff is that they're often irreversible because at the end of it, it makes another hydroxide, and it just keeps going like a chain reaction.
I
That's
see.
why, like, yeah, like this is for aldol condensation, but for hydrolysis, let's say, like hydrolysis of like proteins and things like that, which is hard to do. Um, Adding a base, you can catalyze it with a base, or you can catalyze it with an acid. If you catalyze it with an acid, it'll just hydrolyze one molecule. If you do it with a base, it'll hydrolyze that molecule and then create another base, which then hydrolyzes another molecule, and it keeps going forward. So, you know, acids are good, or are going to be destructive to inorganic things like metals. Bases, though, are what would destroy organic things. So that's just a part of, yeah, you could even see a leaving group here. So this is going to be a chain reaction kind of thing.
Okay, sounds good. All right, this is helpful. I
Yep.
think seeing the mechanism and taking it step by step helps.
Yeah, yeah. So this is okay. So this is something that comes up in, well, I'll talk about like the biochem because it comes up in like glycolysis and gluconeogenesis and stuff. But what we can also talk about here is the kinetic control and the thermodynamic control. Do you remember any of that stuff?
Yeah, so I think that uh kinetic, like I know like kinetic product and like thermodynamic product, and I'm blanking exactly which is which, but I can try to speculate. I know that like the key irreversible steps on like glycolysis are under, I'm gonna say, thermodynamic control, I don't know. And the reversible ones are under the other type of control. Um could be opposite. I don't remember exactly, but I do know that like irreversibility has a specific type of control associated with it.
Sure. So okay. So what you said is true as far as thermodynamics is concerned, but like, so you're talking about, so like irreversible reactions will have their, more negative delta G compared to like reversible reactions, but anything that's So this comes down to what these quantities represent. So here I'll write thermodynamic quantities. So these are things that deal with stability. Okay, so examples include like enthalpy, Gibbs free energy, entropy, all of these types of things that deal with like the overall stability of a molecule. Whereas kinetic quantities deal with speed. When I say that, I mean like rate of a reaction. So if I drew this reaction here, I would get this would be the enthalpy or the bond energy of the reactant, right? And this is the enthalpy or bond energy of the product. And this is the difference between the two. And that will be delta H of the reaction, right? So this is everything I've just named right now are thermodynamic quantities. Now, what's this over here?
The activation.
Uh-huh. So the activation energy, tell me more about it.
It's like required to be like overcome, could be sped up by an enzyme, in order for the react. It's like, I would say like the rate limiting aspect of a reaction.
What exists at that state? Like, we know reactants are on the left, products are on the right. What do you think would
like
be
an intermediate, like a
close? Close? What's something similar to that? Maybe transition state?
yeah, yeah.
So transition state cannot exist on its own. And so the highest energy hump that you see will be that of the transition state. Whereas intermediates can exist on their own, which would make so like what that would look like. So here I'll just write transition state. But let's say we had something like this, like that. So here you would have enthalpy of the reactant, enthalpy. When I say enthalpy, I also mean like bond energy of the product. And here you have transition state 1, and then this little trough or this, valley down here is the intermediate, and then this is transition state 2. So intermediates can exist on their own. They're more stable, so that's why you get a little dip there. So
Yeah.
okay. So overall stability, that's thermodynamic stuff. But things that affect the speed, the rate of the reaction, that is a kinetic quantity. So activation energy, if you reduce the activation energy, you're not changing the energy of the reactants or the products, right? You're not changing their stability. But what you are doing is you're lowering that activation energy, enabling the reaction to proceed at a higher rate.
Okay.
So examples of this would be activation energy. Could also be like, remember when you said like temperature affects everything? Like, could also be temperature, because if you heat a reaction, right, it'll go faster. So things that have to do with speed or rate will be kinetic, and things that have to do with stability will be thermodynamic.
Yeah.
So now in the context of Aldol condensation, let's say we had okay, I'll talk about also like thermodynamic control will occur when I say control, it's like when they ask you for the kinetic control or the thermodynamic control, they're asking which one would, if it's like a kinetic control, that means most of the product will be the kinetic product.
Yeah.
So for control, for the thermodynamic control, it will be the
I
more,
know it forms slower as well.
what's up?
And it forms slower, as of course, like usually like a thermodynamic control. Like later on in the reaction. Right?
Well, it's not going to we can't say anything about speed when we talk about thermodynamics, but we can talk about that once we talk about kinetic. But the things that you can see that would affect a thermodynamic control would be a more substituted intermediate. Okay. So uh so like for instance, if you had like these different carbocations, right? The more substituted ones are more stable. So thermodynamic control you'll see happen with more substituents. Um, and yep, you'll have more negative delta G. And it's preferred at high temperature and strong, small base. And this is just for aldol, by the way. This isn't like,
Okay.
everything, but it's close to everything because, you're going to have, when I say small base, I mean like it's not bulky, right? So that these are going to be things that help cause a thermodynamic control. Things that can cause a kinetic control would be less steric hindrance, um, lower transition states, and I know that I said that temperature can help increase the rate of something, uh, but I guess would help the rate of. So yeah, okay. I guess I said that temperature would help improve or make the rate go faster, but you can also have it like, so if you have it at a lower temperature, you can have it uh not do what the thermodynamic control would be doing. So yeah, I'll talk about that in a sec. So we have low transition state, we have like preferred at low temperature with strong bulky base. So yeah, so let me show you what I mean by that. So let's say we have okay. So let's say we have yeah, let's say we have this. Like that. Yeah, let's, we have two of these. And let's say we add, do you know what this is here?
Torpedo, it's like a bulky
Yep,
group.
true butoxide, yep. So let's add, so like, yeah, let's add this. And I don't know, let's say like low temperature. What do you think we'll get as our molecule? And kind of think about it in the way that I drew it like up here.
Like in the structure, you mean? So I know it should be like the kinetic, because it seems since it's a bulky base and
Yeah.
it's a lower temperature, it's like the kinetic, it's under kinetic control.
Mhm.
Now I have to think what kinetic control would look like.
So,
Um,
yep.
yeah, I'm thinking that uh, the, I'm, oh, I'm unsure. So does it have to do with like which proton gets like abstracted, with the one that's like, on the left or on the right to create that final product?
Uh-huh. Yeah. So let's let's not think of like the mechanism right now, but let's think about, so the way that I drew it like this on purpose, because we can get, you
So
know,
I think like the double bond would probably be like a terminal double bond, like not within the, yeah.
uh-huh.
Mm-hmm.
So if I wanted to show this like this, I could do H, H, like that, right?
Yeah.
With this, getting rid of that to give you just this. Wait, one sec. That, um, I think it'll look something like this. Yeah, what do you think of that?
The one on the right.
Mhm. Maybe it'll be easier if I wrote it like something like this. CH3, CH2, CH3, and then CH3, CH2, CH3. And then this should give us like that.
Yeah. I
So,
see.
uh-huh.
So like the less substituted carbon gets deprotonated.
Yeah, exactly. So this would be your major product. And um, what would be what do you think the minor product would be?
The thermodynamic product?
Oh no, just the minor product.
Yeah. Yeah, I don't know. My guess was that like the if it were like the minor one would be if it were the product that it would happen if it were under thermodynamic control,
Uh-huh.
which would be like the other like the most substituted carbon, so like the
Yeah.
alpha carbons hydrogen being
Yeah.
deprotonated.
Oh yeah, yeah. I just noticed that I had it at first I didn't think the location of these matter, but it does because this is more steric hindrance. So I should put this over on this side. So I'm gonna do that. So that's gonna give me CH2 CH3, and then this is just CH3. So um so you can see that there's less steric hindrance here because like this group and this group are far from each other,
Yeah.
right? So this will be the major product. And this is kinetic control. And the minor product will be essentially what I wrote initially. So that would just be like this. With the bulky side that's on the same side as the other larger
Oh,
side.
I see. I see.
Yeah. At first when I wrote it, I was not thinking because I was thinking that it doesn't really matter which side you put it. But it does because there's a double bond, and the double bond means that they can't rotate freely. So yeah, does matter. So okay, that's your kinetic control, and your thermodynamic control will be like this. So you can see
Yeah.
that's there. And what do you think our end product will look like?
Yeah, just joining. At two.
Like, yeah, so you should get that. So, so okay, so essentially what we drew here were asymmetric ketones because if you had a if you just had a symmetric ketone like with this rather yeah, like this and this being the same, you're not going to have any real differences in terms of kinetic control versus thermodynamic control. um so what we want to see is if we have an asymmetric ketone like we do here, if the major product was a product with a small amount of steric hindrance, that will be the kinetic control or the kinetic product. And if the major product is more substituted, it would be more stable, and therefore it will be your thermodynamic control or your thermodynamic product. So, yeah. What do you think?
Right. Yeah.
So,
Makes sense. Yeah.
yeah. Oh yeah, and then I forgot that this would be like tert butoxide, and then this would just be uh like
OH, not any OH.
yeah, something like this, like hydride or whatever. High temp. So yeah, okay. So you have so you have that, and yeah, what are your thoughts?
Makes sense.
Okay. I'm gonna get the okay, this is good too. So here we have base-catalyzed aldol reaction. You have your alpha carbon. You're adding strong base.
It says fail to load for me. I'm not able to see it.
All right. So okay, I'll probably have to exit and come back, but let me just I'm just gonna add the examples of this in the metabolic pathways, because that's you're gonna see this in that context. So for instance, you would get let's see. So you would get in glycolysis, you will have what did it look like? It looked like I'm just gonna put a P with a circle around it to indicate phosphate. Um, you recognize this molecule? So think of a molecule in glycolysis that has two phosphates.
Like fructose 1,6-bisphosphate.
Yep. Good. All right, and then what can happen here is this can break up into these two molecules. This is I think it's glyceraldehyde phosphate, GAP. and DHAP, right? So yeah, so this is kind of like a reverse, I guess, or I think it's called retro aldol. And that's what you see in glycolysis. In the Krebs cycle, you will see some.
Does
Yeah.
it say what reagent is used for the retrohaldol?
Oh, so it'll likely be like water and something else because you're doing the opposite. Um, so let me see in my.
And this is reversible, so I'm assuming you also have the normal aldol condensation.
Yeah, one sec. Actually, yeah, I don't even. Well, I didn't write anything for that. Let me see. Um, all I see is just like an enzyme.
Mm. It says like for me, like Google search says that it's reversible in the presence of acid or base catalyst.
Uh-huh.
Uh, like just I guess it depends perhaps on like what type of aldol condensation um to reverse it, but it has to be an aqueous solution.
Uh-huh. Yeah. I
Um,
mean, my guess would be water because aldol condensation is dehydration synthesis, and then this is a hydrolysis, so my guess would be water. But from what I see, I just see like aldolase listed. So yeah, I'll try to get more information on that for you.
yeah.
But yeah, for the uh yeah, in the Krebs cycle, you would have this um
Acetyl-CoA,
plus yeah, plus
salicylic.
mhm. Yep, so you get oxaloacetate plus oh, that's the other way around. This is acetyl-CoA, oxaloacetate, and you get S-citral CoA. And then the last one is in gluconeogenesis. So you will get basically, well, what do you think you'll get?
You can get the fructose 1,6-bisphosphate again.
Exactly. So yeah, I don't have to write it out, but yep, DHAP plus GAP, fructose 1,6-bisphosphate.
Yep.
So yeah, so you'll see this type of yeah, you'll see this type of reaction, aldol and retroaldol, in these metabolic pathways. And the kind of like shortcut method of doing the, I mean, like I have the mechanism here for you also, but yeah, the shortcut method like this. I'll put it in like the red box.
A box, yeah.
Yeah. So that could be the like shortest way for you to do it.
Yep.
Yep.
All right, sounds good.
Mhm.
I think that I am very tired,
Yeah, no,
so
of
I
course.
should try to get back home, but I'm going to export this out.
Go ahead.
And just for this weekend,
Mhm.
I think I'll be taking either probably on Sunday the AAMC full length,
Yep.
probably the 2022 one, so like full length 5 or full length 4, one of those two.
Yeah. Which one has is did you take a longer time ago?
Probably full length 4.
Yep.
I don't remember exactly. It was similar. I probably took them like one after the other.
Got it.
Back in like
Uh-huh.
last year, April.
Got it. All right, awesome. Yeah. Good luck. And whatever the score turns out to be, like don't treat it with so much weight, like you know, uh because there's going to be probably some proactive interference and stuff like that. But I still think you'll do fine. And and yeah, maybe like tomorrow have just like a rest day or something, and then take your test, take the practice test on Sunday.
Yeah.
Yep.
And just for the following week, since I'm not working,
Yep.
I would prefer, and maybe you too, that we meet earlier in the day.
Mhm.
Yeah.
Yep. So the like, let's see. So for Monday, I'm free at 5 p.m. Does that work?
Yeah, that works for me.
Okay.
We can meet then and just go there.
Yeah. Yeah. So, okay, awesome. So yeah, I'll see you on Monday, and yeah, good luck on your test. And yeah, and then, you're taking your test on Sunday, so tomorrow just, have a rest day.
Yeah. I'll probably be doing some Anki, but yeah.
Yeah, so Anki, that's it though. All right, awesome. So I will see you on Monday. Good luck, okay?
Thank you. Bye.